sudden got very loud. In case that intro does make any sense, I actually wear two hats. I'm also an academic, and I'm a professor of computer science at Princeton. But today I want to talk about what we've been doing at IOBeam and somewhat of our lessons about using Spark to deploy IoT applications. So let me start for a second about kind of why all of a sudden we see a lot of interesting things, and perhaps Gartner says IoT is at peak hype. I think it's really a confluence of three things and kind of technology trends that have developed over the last 10, 15 years. First is the rise of, in some sense, ubiquitous sensors. We have that through 3D printing, crowdfunding campaigns, and actually supply chain changes that makes it very easy to build hardware at scale. Second, really, that came through the first wave of big data, which is big data at rest. We've had the rise and popularization of machine learning. Ali called this yesterday the democratization of big data, and we kind of see that now bring ourselves into what's happening in IoT. And third, we have the desire and finally the trust of computing systems to do it in a more automated fashion. There is a scale, this is the rise of singularity, but I think that this is more that we're starting to think about these systems in real time, either to give alerts to operators or kind of to complete what we think about the sense, analyze, act loop and control our systems directly. Now, at the core of all these three things is really the need for data analysis. Now, the interesting thing is when you hear about IoT, for most people that means consumer apps. While it's great, or consumer IoT, smart homes. While it's great that we could control our light bulb from our phone, in fact, I'd hate that, but that's a different story. I think the interesting thing is actually when we have these type of applications that we really couldn't do before with just a switch on the wall. And there are four, I think, great examples of where data analysis is kind of the killer app of these programs. These are actually all customers that run on IOBeam. The first, which is really big, is predictive maintenance, where you could actually detect, and there's really clear ROI here. You could detect when things go bad. For example, one party actually puts vibration sensors on motors and then do kind of fancy spectral analysis of vibrations and determine when they think a motor is going bad. These are multi-million-dollar motors each. Second is something health and fitness. It's great that Fitbit could track how many steps you had. But we have other people who are building BLE devices to put in weight racks and barbells. And as you pick up a barbell and start moving it, they track the 3D motion data, determine what exercise you're doing. Because they classify that, they could then count reps and also make suggestions to you automatically about how your form is wrong, kind of a personal virtual trainer. Smart cities are really a major part. We're here in New York City. I'm going to talk more about some smart cities apps. We could actually put sensors on buses, and then rather than needing to really dense deployments all around the cities, we could drive these sensors around the city. And once we have sensor platforms and devices out there, it's really cheap to put more and more sensors on those devices. And so now we use one platform for a whole variety of things, from traffic analysis, air quality monitoring, environmental sensing, noise pollution, pedestrian safety, et cetera, et cetera, et cetera. And finally, you hear a lot of things with smart grid. You might actually complete the actuation loop. You might control the consumer home as the demand response to actually supply side capacity or the spot price market and kind of do that all in real time. Okay, so these are kind of some examples of how we're doing actually real-time analysis. And what we've been doing is actually making Spark as there's really this powerful framework because SQL queries are not going to enable us to do a lot of what we talk about up there. And certainly if you think about the analytics from the web and mobile world where you're just counting sessions, it's also not going to give us the type of analysis we want. So here we need rich analysis for these type of applications. So can we just take Spark and move it directly to IoT? In many cases, it provides a great platform. And rather than sing its praises, I actually more want to talk about some of the challenges we found. And a lot of these really arise from that Spark arose more as a batch processing framework. And as it went into some of the settings like a stream processing framework, it was able to get unification, but it still adopted some of the assumptions that more came from the batch world. So let me talk about some requirements and challenges, and really this talk is just going to be talking about more detail these challenges and kind of give you some suggestion about how we would ameliorate them. So first requirement that we'd have in IoT is that we'd want one IoT application to actually perform tasks at really different time intervals. The challenge is then that we want to be able to handle the full spectrum of batch to real-time analysis. Now, you've heard many times that Spark is kind of good at unifying them. What I'm going to talk about is it's good at unifying them from, now I have Jan, hopefully he won't criticize anything I say, good at unifying them from a programming abstraction, not as much from a data infrastructure abstraction. I'll talk a little bit more about what we mean by that. Second requirement is that we have devices that send data at varying delays and rates. What this means is that we want to be able to handle delayed data transparently and process many And we also have the issue that we interestingly want to think about how does it mean to process many low-volume independent streams. Interesting, a lot of the scalable processing is thinking about really high-volume streams, but now we actually have a lot of independent low-volume streams that we want to process. Number two, perhaps, this would have been more impactful if Databricks didn't manage to steal most of my thunder by talking about all their structured streaming. But I think that one of the things that we're thinking about, we're still in different settings, so it actually raises some interesting questions about how we can do this a little bit differently. And third, with an organization, and particularly within a hosting platform like IOBeam is, you actually have many IoT applications that want to run concurrently. And the challenge is that you want to achieve multi-tenancy, interestingly, for low-volume applications, and yet still achieve high utilization. Right? Okay. As an academic, I kind of hate whenever I see McKinsey data, but I feel necessary to include it anyway. IoT is worth a lot of money, but I think the key part is that most of the data remains unused today. And so again, the question, like I think you hear a lot of platforms talking about, is how can we make it easier to allow people to analyze that data? Okay, so what I kind of want to talk about, the main focus of this talk is, what I think we need is actually a way to have both programming and data infrastructure abstractions to make it a lot easier to do these type of tasks. And Spark, at least, is this great programming abstractions for unifying batch and real time. And I want to talk a little bit about, though, what we might need from infrastructure. So what do I mean by this first one? That it supports a full spectrum of batch to real-time analysis. Let me give you an example, though, of an IoT application. Here we have a sensor platform deployed upon buses. Just as a scale, there's about, at any one time in New York City, this is in San Francisco, we have about 5,000 buses at one time. If we want to do things like hyperlocal analysis, let's say 100 meters by 100 meter squares, it translates to about 50,000 independent locations around the city, each which would be generating unique streams of data from the buses that are driving around the city. Okay, so you could think we have these sensor platforms on these buses. We do fires happen, temperature sensor, want to report that immediately. That's as real time as we can get. We might want to take the bus and location updates, feed that to users who actually see where their bus is. Maybe on a 15-second, and I think the MTA actually reports that around 15 seconds today. Traffic conditions, we want to calculate, say, every minute. We then feed back to users about when their next bus is supposed to arrive. Track things like environmental conditions, air quality on maybe a 15-minute or 30-minute horizon, maybe do traffic optimizations daily or weekly. So what you actually see is, if we think about where this originated, we started in a world where we actually perform batch processing through MapReduce in the hourly or nightly world. And we did real-time stream processing initially on a tuple-by-tuple basis. What we have in real settings is this continuum of types of analysis we want to do. But if you think about it, even though we have this continuum, what we and let me give you an example of one of the nice things about Spark is it simplifies programming. So in this example, you get a D stream of readings. And we might write a little application that quickly filters out a set of bad temperatures, creates a stream of triggers, and these are then going to be sent off for real-time notifications. We similarly could do things like compute mean temperatures over windows and generate a stream of these mean aggregations. And the nice things is if we ever decide to change our things where instead of computing mean temperatures every 5 minutes, we compute every 30 minutes, you just could change the window size in Spark's programming model. So this seems really nice. One of the things is that, however, is that programming abstractions are not necessarily the simple thing as the data infrastructure abstractions, the data sources that we're reading from. So even though this supports the continuum, what we're actually going to be doing is reading data from sources that are really, again, on these two extremes. We're going to be using data streams as inputs coming from something like Kafka or Flume, or we're going to be using something like a file abstraction on HDFS that themselves are, there's not really as much a continuum there. And so users in their programs are therefore going to more align with, or are going to have to specify their kind of sources and sinks, and that's going to more place them in a certain world. So, really what we're talking about is one of the problems is that these things also aren't static, right? So frequencies can change as the programs evolve, as products evolve. You might start things at an hour, and then you start wanting to compute things every 30 seconds. And the other big thing is, and this has been talked a bunch at Spark at the summit. By the way, the timer is not actually on, so if Okay. That you might do things like take a 5-minute mean and actually compare this to a trailing mean. So you want to join real-time data with historical. Now, one option is you're just keeping this as a Spark RDD in memory, but give me any size memory and I'm going to give you an example of a program that's going to exceed your memory. Rather than compute via the hourly mean, I want to compute via the last week's mean. Or I want to compare my retail mean against what I was actually seeing last holiday season a year ago. And third, kind of a key part of this is, and I want to talk about this more, about supporting data for backfill. And so really what you might have noticed in the last picture that we kind of showed this little, I hid some things up here, where we're actually trying to provide this data series abstraction as part of because we own the platform and then can make decisions about the platform, where a programming framework wants to support many different types of infrastructure, we could actually simplify that process as we expose our data abstractions to people using the platform. So let me talk about a second problem, which is kind of related, which is how do we actually handle delayed data transparently? And if some of you saw the first keynote, this talked about a simpler thing, but just as a little history, streaming databases go back to about 15 years now, a lot of times used earlier in financial trading, and it really came out of the SQL world. It came out of the relational database world. And so you basically change the SQL query to deal with what in some sense is an unmaterialized view that is just a window. And you could have a tumbling window where they're disjoint, or you could have what you call a sliding window where they're overlapping. And in Spark, they generally have sliding windows where you specify the window size and the slide period, but if you set the slide period equal to the window size, you basically get the equivalent of a tumbling window. Okay. Now, the key thing with this is that you could think about how you define these windows. They were originally in streaming databases defined over a number of tuples over a time period. A key part is that they all basically used, from the beginning and including in Spark streaming, the arrival time of the tuples. Now, the problem is this actually might have made sense and might not have been that much of a difference if data basically was born, was used, and died all inside a data center. Really optimized for high bandwidth and low latency. Yes, things can be delayed, and that's what it was talked about this morning, but it's much less of a problem than when we actually think about IoT data where it's generated by the edge. This delay could be because we have seconds of congestion due to network effects. Particularly if we're looking to track moose in northern Canada and we're on 2G, you probably could have fairly high latencies pushing this data back to your data center. It could be minutes due to duty cycles. This is actually a device coming out of a startup out of Princeton on Smart Ag. It's solar powered. They duty cycle the device based on the amount of available data power. Many of you may or may not know the largest power hogs in your mobile devices are your screen and your network. These things don't have screens, so your big resource is your use of network consumption. So you're going to manage that use of network based on your available power, your power budget. And third, you could have minutes to hours due to intermittent connectivity, trains moving between stations. You might have a cellular link for real-time critical alerts, but if you're collecting a lot of just sensor data, you're actually going to transmit it via Wi-Fi when you pull into a station. Similarly, in retail environments, you have Wi-Fi. You think that's great. Great connectivity, except you find out a lot of retail environments would shut down their networks at night. So the data is going to be delayed by 8 hours till the next morning. So what this really means is that windowing data by arrival time has very little semantic meaning when you actually try to process it. And so one thing what we kind of want is you want it by generation time or event time, it was called this morning, not actually by arrival time. So kind of transparent to the developer, what you actually are doing effectively is as you're processing streams of data, you're filtering them in windowing time by their event time, not actually by their arrival time. And then perform aggregations on that set that's actually corresponding to timestamp time. And what this means, of course, is when you do something like a join, you're still operating on the same, the semantics are in terms of the same timestamp. This particularly is important if you think about a kind of a lambda, what some people call a lambda architecture, where you might do batch processing. Because the batch processing is actually, because it's taking these big batches, will be on terms of event time and generation time. So if you then try to join something in terms of event time against something in terms of arrival time, again, the semantics don't really make much sense. Now, kind of the holy grail of this a little bit, and this is, I think, a lot of the challenges we talked about this morning, was that we want something like Backfill to not actually change the semantics. That data can arrive late, but we want to consider, it's interesting, this morning you talked about starting from time 0 to time n. You could think about actually defining these windows where I'm expressing kind of in a similar way. You take much larger windows of time before which you kind of abstractly pass this through some filtering and windowing before going down to the simple aggregation. Now, the interesting thing is because you actually, if you are a provider that provides a data infrastructure to a programming framework, you actually kind of control the data storage. So you actually know, for example, if this is recent data, you could be pulling it from your message bus because you know that that data originates there, or from just Spark RDDs, or if it's actually very historical data. So if a piece of data comes in late and you pre-compute an aggregate, you actually want to fetch that aggregate or even raw data because you want to fully recompute the calculation because that is a type of holistic calculation that can't be incrementally updatable. You could pull that out of some historical store and combine that with the new data that's actually coming in late. And so these are all nice things that you could do if you kind of own and provide a common data series abstraction to the programming framework. Okay, third, and this is kind of much more of a minor, somewhat more of an optimization in specific IoT. But interestingly, in IoT, a lot of times the first thing you're doing is processing many low-volume independent streams. So in Spark parlance, these are often narrow calculations rather than wide calculations. And in many cases, you actually also want to maintain state across batches. And this is just kind of a pattern that we found to be quite useful. So in the kind of the smart cities or smart ag, you might want to basically map certain individual tuples to good and bad conditions. The ground is dry, I want to water it. The ground is wet, stop watering it. Now, a lot of times what's important here is actually the transitions between these two good and bad conditions. And so you want to do something like alert on condition transitions, i.e. tell my center hoe watering to turn on because the ground needs water, or have it stop watering or stop fertilizing it because we have enough out there. Now, again, because data can be sparse, if we take a fixed window size in Spark streaming, we actually don't know if there is going to be data from this particular sensor in that window size. So we actually need to think about maintain state in some sense about what the last condition was, right? Now, Spark's model was really, kind of where it really innovated was you had really wide streams, large quick streams, ad impressions, market feeds. And kind of its key contributions was basically taking these streams, partitioning these things over lots of workers. And then we need to think about shared state and use functions like update key by state, which actually transforms the RDD and therefore makes state available to different devices across the cluster. This has many great uses. The one downside is it increases the data lineage, which means that things like checkpointing become more expensive. Okay. But in IoT, if we actually have many independent streams where our partitioning function, let's say, is across devices and therefore these things are treated in a kind of a narrow fashion, in many cases, we actually only need to maintain state within that individual stream, not across the whole stream, at least for this type of calculation I described. And so each worker actually can handle many of these streams, not multiple workers per stream. And therefore, we found it actually easier to use kind of other type of things like just language data structures to maintain state within that worker, as opposed to actually transforming the RDDs to share state. The advantage, of course, is without transforming the RDDs, we actually don't increase our lineage, and therefore checkpointing, we don't actually add increased checkpointing costs, which is something to kind of think about to ensure good performance. Okay. And the last thing I want to talk about, which again kind of has the notion that in many IoT applications, even though you want to respond quickly to events, sometimes those applications are actually relatively low volume, is that how do we do multi-tenancy? So we take a step back and actually think about where multi-tenancy originally arose in the batch processing world. The goal of scheduling in batch processing world was to minimize your time to completion. If you have two apps that both independently would take 5 minutes, you'd rather run one to completion first, it finishes at 5 minutes, then start the second one between 5 minutes and 10 minutes, as opposed to running them both in parallel, getting half the resources, and both taking 10 minutes to complete. Greedy scheduling. So in Spark, we have kind of one worker is assigned to one server core. This is kind of the right design for high volume processing. And all these systems in Hadoop and Spark and all the schedulers basically are kind of assigning these tasks to server cores. And as soon as they complete, you assign new jobs. The problem, if we want to think about stream processing with, and this really arises when we think about low-rate apps, as you might have a company that deploys lots of applications in-house, or you're a hosting platform that actually wants to allow lots of people to run on you, is that, again, we have this thing about one worker equals one server core, but a lot of people are going to be having apps that are going to be used really fractions of actually modern, the speeds of modern servers, right? And so we're really, and the first thing, if you think about actually what the batch processing is doing, it's doing the equivalent of time division multiplexing, right? And if you think about what we have now, we actually now have a lot of idle cycles because you're giving time slots to people and they're not using them. So what we actually found to be quite useful is rather than thinking about let's like completely re-change the way Spark might actually do allocations, which had a lot of architectural implications, what we've actually done is we as part of infrastructure in general, we were a completely kind of containerized infrastructure. So we actually run all of these kind of things in containers, and then it basically exposed to Spark virtual cores. And so now we actually could use OS resource limits and even modify those resource limits that we give to each virtual cores. So we could actually take an unmodified scheduler, but now they're actually being assigned to virtual cores rather than physical cores. We could actually achieve much higher utilization in our cluster. Okay, so last thing I just want to end with is, one of the things we really found is thinking about how can we combine the unified programming model of Spark with a more unified data infrastructure. And what we find in this infrastructure, we need many different things like processing, storage, security, monitoring, triggers. And what we started calling this is, as a way to build IoT applications is this device-model-infrastructure framework. So many people have different devices. These are never going to, I think, unify like we have in the mobile world to two platforms. These are continuing to be very different. Some people need low-power devices. Some people need cellular, some Wi-Fi. So there's physical constraints, fundamental physical constraints that are going to make these devices different. So we should continue to make an infrastructure and programming agnostic about the actual hardware. And we should allow our data science team to program, and I think this is a lot of where Spark has really innovated with, to program our unified abstractions and not worry about the infrastructure. And I actually, and one of the key things it needs to do is be able to take things like both program on the raw data, output derived data, and take that derived data back as historical data into your programs, and also do things like expose outputs, including the ability to query that derived calculations in raw data, and also to push alerts to other systems for automation. So my one product slide is, in some sense, this infrastructure is what we've been building at IOBeam to kind of make it a lot easier then to develop Spark models and analysis on your IoT data. If anybody is more interested in actually this infrastructure came from talking to about 200 different IoT companies and working with them and how they've been building their systems. So if anybody is curious about, we recently released a white paper about the different things to think about if you decide to build your own kind of infrastructure, what type of things you might think about. So any questions? Okay.
So you talk about multi-tenancy from the perspective of the compute, but what about
resource utilization? Yeah.
Yeah. What about multi-tenancy down potentially to the bottleneck of disk and network, and how do you allocate resources in a 10,000 jobs simultaneously, and the bottleneck becomes local disk?
So there's a couple different answers to this question. The interesting thing, wearing my academic hat, I've actually done quite a bit of work on how you would even do resource allocation on shared disk for storage systems. I would say that, and I'm happy if you give me information, I could point you to some of the papers we've published about this kind of work. I would say that part of these answers, I think pragmatically you could actually handle as a hosting provider through the billing practices you develop. So for example, really the key part that I touched on here, which was difficult, was dealing with low volume applications. With high volume applications, actually, a common practice, if you look at what Amazon's doing today, is you're actually giving independent disk and you could kind of hard provision IOPS on that to various high rate flows. The challenge generally is when you're at the low rate, because it's actually very hard to give it's hard to provision resources to give kind of SLAs on performance when you have kind of very low instantaneous use. The short answer is that some of this will actually be that you do separation of your disk resources by customer, by apps, and then you have shared pools when you have relatively low rate apps, and you kind of reflect that in your billing models. But if you come up after, I'll point you some interesting research we've done. It's more that, the question is it worth biting off that complexity for things that are handled in other ways?
Yeah. Great talk. So 2 quick questions. Have you looked at the index RDDs as a way to efficiently backfill?
I have not yet. I'm particularly after the talk this morning, I'm more interested in finding out more about what you're doing there too.
So the other question I have is that in this
I'll say one thing. One thing we're worried about in general is the extent to which we are not storing large amounts of index data, RDD data in memory, because of concerns about costs and other things.
Got it. So the other question is that you mentioned, I think it's a great point. You have a lot of small streams, but and you do computation on each of them, and the current Spark model is 2 cores granularity for that. What about the heterogeneity? Do you have many cases in which you are going to do different processing on different streams?
I think there's, sure, there are different, generally what we find is that there's different types of streams as inputs, and you write different programs on these different types of streams. I'm not necessarily sure the connection of that question, though, to...
I was curious about the model, right? It's like when you have one model, you need to have the same computation on different sources of data.
Mm-hmm. Yeah, so certainly, for us, the people who are building the IoT applications, part of where this comes about is if you look at a lot of these different verticals, the people building these interesting applications are not at their core, software engineers. A lot of times these are coming out of people who are from these verticals, so ecologists building farming applications, that kind of thing. So a lot of times they have specialization with hardware and they have specialization with data scientists, but they have less in terms of software infrastructure, which is where we kind of are coming in. Now your question is there are certainly things that we have done to general IoT telemetry, whatever, that we build as kind of a service. When we go to the extreme, when people is doing vibration sensing on a motor, that's really specific to application, they're building it. So in that case, yes, they will write different applications, but in some sense that's really on the people using the platform who are writing the Spark apps. I think that one example of the state was one thing that was more about programming the application, where the rest of it was more on the infrastructure layer.
All right, let's take one more question, and then we can have other questions offline. Over there.
So, in this multi-tenancy problem, are you developing your own? You can think of Spark like an application task scheduler, and
Sure.
separate that from your resource scheduler, your memory, your disk, your network.
Yep.
Are you building infrastructure for the resource scheduling and management, or are you just using what's existing in Spark?
Well, so there's 2 levels of this, right? There's the Spark orchestration layer, which I'm using, and then there's the basically cluster infrastructure. I could say we use kind of Kubernetes for that, and so we're actually using resource management in Kubernetes to then give virtual cores to applications that could then, so we're managing it in kind of 2 different layers.
All right,
Okay,
let's have
thanks.
one more round of applause for Mike Friedman.